right now. As you watch this video, light from stars that died billions of years before Earth existed is hitting your eyes at 670 million miles per hour. You think you understand how big things can get, but everything you believe about size is completely wrong. We're about to journey through objects so dense that a sugar cube would weigh as much as a mountain, past structures so vast that light takes longer to cross them than humans have existed on Earth, and into regions where space itself grows faster than light can travel. If you're ready to have your understanding of reality completely shattered, hit that subscribe button because what comes next will change how you see everything forever. The numbers we're about to encounter will break your brain. We'll discover objects spinning 700 times per second, explosions that create more energy in 1 second than our sun makes in a million years, and structures so enormous they shouldn't exist according to our best theories of physics. Every reference point you use to understand size is about to become meaningless. Your house, your city, your entire country will shrink to nothing compared to what's really out there. Prepare yourself for a journey that starts with the ground beneath your feet and ends at the very edge of everything we can ever know. This is the true scale of our universe. You are standing on a ball of rock right now, spinning through space at 67,000 miles per hour. You think Earth is huge because it takes you hours to drive across your state and a full day to fly to another continent. Walking to the store feels like a journey. These everyday experiences build your entire understanding of what big means. But here's what will destroy everything you think you know about scale. Earth only seems massive because we experience it one step at a time. Our brains evolved to understand distances measured in miles, not millions or billions of anything. When someone says a billion, your mind treats it exactly the same as a million. They both just mean really big number to your survival-focused brain. But the difference is staggering. 1,000,000 seconds equals 11 days. 1,000,000,000 seconds equals 32 years. Compared to what's actually out there, Earth is smaller than a speck of dust floating in a cathedral. If you could shrink down everything in space, Earth would become invisible to your naked eye before you even left your cosmic neighborhood. The moon looks small enough to cover with your thumb, but it sits 240,000 miles away. That's like stacking 10 Earths in a row and still not reaching our closest neighbor. Your brain cannot truly grasp what this distance means. Evolution never equipped us to understand such scales. If Earth were a marble, our entire solar system would still be smaller than a city block. And our solar system is just one tiny point in a galaxy containing 400 billion stars. Every scale you think you understand is about to be obliterated. The big things in your daily life are about to become utterly meaningless. Your house, your city, your entire country will shrink to invisibility compared to what we're approaching. But compared to what comes next, Earth actually looks like a giant. Earth's atmosphere is trying to crush you right now with the weight of an elephant. Every square inch of your body experiences 14.7 pounds of air pressure. You don't feel it because you've lived inside this invisible ocean your entire life. But this crushing blanket of gas that keeps you alive only extends a few dozen miles above your head. Space officially begins at 62 miles above sea level. That might sound close until you realize what 62 miles straight up actually means. If you stacked average people on top of each other, you need almost 60,000 humans to build a tower reaching space. Picture that tower stretching beyond clouds, beyond where jets fly, beyond where weather exists. Commercial airplanes cruise at only 6 miles high. Even at that altitude, you die in 15 seconds without air pressure. Your blood would literally boil, but you're still only 1/11th of the way to space. Mount Everest, which kills experienced climbers regularly, reaches just 5.5 miles up. You need to stack 11 Mount Everests to reach space. Here's what makes this distance mind-bending. If Earth was shrunk to basketball size, The atmosphere would be thinner than paper wrapped around it. All the air you've ever breathed, every cloud you've seen, every bird that's flown exists in this impossibly thin shell. The International Space Station orbits at 250 miles up. Astronauts there aren't floating because there's no gravity. Earth's gravity at that height is still 89% as strong as on the surface. They float because they're falling around Earth at 17,500 miles per hour, continuously falling but never hitting ground because Earth curves away beneath them. The space station seems impossibly far away, but it orbits closer to Earth's surface than the distance between New York and Washington, D.C. You could drive there in under 3 hours at highway speeds. Yet this tiny step represents humanity's greatest achievement in space travel. Light from the sun hits your face 8 minutes and 20 seconds after leaving our star's surface. In those 8 minutes, that light traveled 93 million miles through empty space. But here's what will melt your brain. In the same time, light could circle Earth's equator 7 times complete. This reveals something incredible about the sun's size. Our star is so massive that light, the fastest thing in the universe, needs over 4.5 seconds just to travel from one side to the other. Light can circle our entire planet in 1/7 of a second, but needs 4.5 seconds to cross the sun. The sun could swallow over 1 million Earths and still have room left over. The sun contains 99.86% of all mass in our solar system. Everything else, Earth, Jupiter, Saturn, all planets, moons, asteroids, and comets combined, makes up just 0.04%. If the solar system were a giant pizza, the sun would be everything except tiny crumbs scattered around the edges. The sun's surface reaches 10,000 degrees Fahrenheit, hot enough to vaporize any material on Earth. But the surface is actually the coolest part we can see. The core burns at 27 million degrees. At those temperatures, hydrogen atoms smash together so violently they fuse into helium, releasing the energy that keeps you warm. Every second, the sun converts 4 million tons of matter directly into pure energy. This has been happening for 4 billion years and will continue for another 5 billion. The energy our star produces in 1 second could power human civilization for hundreds of thousands of years. Despite this incredible power, the sun is remarkably average. Astronomers call it a yellow dwarf star. In our galaxy alone, stars exist that make our sun look like a birthday candle next to a forest fire. Some stars burn so bright they consume themselves in just millions of years instead of the sun's 10 billion-year lifespan. Pluto sits in eternal darkness at the frozen edge of everything you call home. Even though we no longer call it a planet, this distant world marks the boundary of the solar system most people imagine. But Pluto isn't even close to the real edge. The actual boundary stretches so far that it makes the distance to Pluto look like a walk to your mailbox. Pluto orbits our sun at 3.7 billion miles away. Light from the sun takes over 5 hours to reach this frozen world. From Pluto's surface, the sun appears as just a bright star, providing barely more warmth than starlight. Temperature there never rises above -375 degrees. Liquid water cannot exist. The atmosphere is so thin it would be considered vacuum on Earth. But here's what destroys your sense of scale. Pluto represents only the inner edge of our solar system's true boundary. Beyond Pluto lies the Kuiper Belt, a ring of icy objects extending another billion miles outward. Beyond that stretches the Oort cloud, a spherical shell of comets reaching halfway to the nearest star. The Oort cloud extends 50,000 times farther from the sun than Earth does. If you could shrink our entire solar system to the size of a grain of sand, the nearest star would still be over a mile away. Picture holding a grain of sand, then walking over a mile to find the next grain representing the space between stars. Our fastest spacecraft, Voyager 1, launched in 1977 and travels at 38,000 miles per hour. After 47 years of continuous flight, it has barely left our solar system. It won't come close to another star for 40,000 years. Even at light speed, it would take over 4 years to reach our nearest stellar neighbor. The space between stars contains almost nothing. You might find 1 hydrogen atom per cubic foot in the emptiest regions. Earth's atmosphere contains trillions of atoms in the same space. Our galaxy is eating other galaxies right now. As you read this, the Milky Way slowly devours smaller galaxy groups, stretching them into streams of stars that wrap around us like cosmic spaghetti. This process has been happening for billions of years, and we're just beginning to map this stellar graveyard scattered throughout our galactic home. The Milky Way contains between 200 and 400 billion stars. Each one is a sun, potentially hosting its own family of planets. If you could count one star every second, it would take over 12,000 years to count them all. But the mind-breaking part isn't the number of stars. It's the distance between them. Our galaxy measures 100,000 light-years from edge to edge. Light traveling at 670 million miles per hour needs 100,000 years to cross from one side to the other. Voyager 1 would need over 1.7 billion years to make the same journey. By then, the sun would have burned out, Earth would be gone, and the galaxy would have completely changed shape. We're not sitting still inside this structure. Our entire solar system orbits the galactic center at 515,000 miles per hour. At this incredible speed, it still takes 230 million years to complete one orbit. Dinosaurs lived and died during our last quarter orbit around the galaxy's center. The center hides a supermassive black hole called Sagittarius A star. This monster contains 4 million sun masses crushed into a region smaller than Mercury's orbit. Stars near the center orbit so fast they complete full orbits in just 16 years, experiencing gravitational forces so extreme that time runs slower for them. Our solar system sits 26,000 light-years from the galactic center, roughly halfway to the edge. We live in the Orion Arm, a minor spiral arm containing just a tiny fraction of the galaxy's stars. Most of the Milky Way's mass exists in regions we will never visit. A star named Uy Scuti is so large that if you placed it where our sun sits, it would swallow Mercury, Venus, Earth, Mars, and extend past Jupiter's orbit. Light needs 9 hours to travel around this monster's circumference. If you could drive around Uy Scuti's equator at highway speeds, the journey would take 9 million years to complete. Uy Scuti belongs to red supergiants, stellar monsters in their final death phase. When a star contains more than 25 times our sun's mass, it burns through nuclear fuel at incredible rates. The more massive the star, the shorter and more spectacular its life becomes. While our sun burns steadily for 10 billion years, Uy Scuti exists for only 10 million years total. Despite being 1.7 billion times larger than our sun in volume, it only contains about 30 times more mass. This means the star is incredibly thin. Its outer atmosphere is so sparse it's essentially vacuumed by Earth standards. If you could stand inside Uy Scuti's outer layers, you might not realize you are inside a star. But Uy Scuti isn't even the most massive star we know. That title belongs to stars in the R136 cluster, 65,000 light-years away. These monsters contain up to 300 times our sun's mass packed into much smaller volumes. They burn so hot and bright they blast their outer layers into space with stellar winds moving thousands of miles per second. The most massive stars push theoretical limits for stellar formation. Above a certain mass, stars become so hot that radiation pressure prevents them from gathering more material. These giants burn through fuel so quickly they exist for only millions of years before exploding as hypernovas, explosions so violent they can be seen across billions of light years. When Scuti finally dies, it will explode as a supernova visible during daytime on Earth. Despite being thousands of light years away, the explosion will outshine our entire galaxy for weeks. A neutron star called PSRJ 1748-2446 rotates 716 times per second. In the time you blink once, this stellar corpse completes over 200 full rotations. Its equator moves at nearly 100 million miles per hour. Any faster and centrifugal force would tear the star apart. Neutron stars represent what happens when massive stars cause collapse under their own gravity. In less than 1 second, a region the size of Earth gets crushed down to a sphere just 12 miles across. The collapse is so violent that protons and electrons get smashed together, forming neutrons. What remains is the densest matter in the known universe. A neutron star contains more mass than our Sun compressed into a volume smaller than Manhattan. The gravitational field at its surface is 200 billion times stronger than Earth's gravity. If you could stand on a neutron star's surface, you'd weigh the same as Mount Everest. The escape velocity is 100,000 miles per second, nearly half the speed of light. But density truly breaks your brain. 1 teaspoon of neutron star material would weigh 6 billion tons on Earth. That's more than all cars, trucks, and buses on the planet combined, compressed into something you could hold in your hand. A sugar cube of this material would weigh as much as a mountain. The magnetic field around neutron stars is 1 trillion times stronger than Earth's. This intense magnetism funnels charged particles along magnetic poles, creating radiation beams that sweep through space like lighthouse beams. When these beams point toward Earth, we detect regular radio wave pulses. That's why we call them pulsars. Some neutron stars are even more extreme. Magnetars have magnetic fields 1,000 times stronger than regular neutron stars. These fields are so intense they'd erase every credit card on Earth from 100,000 miles away. A magnetar's magnetic field energy could power human civilization for 1 billion years. The observable universe represents just a tiny bubble within a cosmos that may extend infinitely in all directions. We can only see light that has had time to reach us since the Big Bang, creating a spherical boundary 46 billion light-years away. Beyond this cosmic horizon lies more universe, potentially infinite in extent, forever hidden from our view. Light from the edge of our observable universe has been traveling toward us for 13.8 billion years. But cosmic expansion carried those distant regions much farther away during the light travel time. The regions that emitted the cosmic microwave background radiation we detect today now lie 46 billion light-years from us, well beyond what we can ever reach. But here's what makes the universe's true size mind-boggling. Cosmic inflation theory suggests the entire universe is much larger than the part we observe. During the first fraction of a second after the Big Bang, space expanded exponentially, stretching a region smaller than a proton to grapefruit size in less than a trillionth of a trillionth of a trillionth of a second. Conservative estimates suggest the entire universe is at least 10 to the 23rd power times larger than the observable portion. This means if the observable universe were shrunk to light bulb size, the actual universe would still be larger than Earth. More extreme inflation models propose the universe could be infinitely large, containing infinite matter and energy. An infinite universe would contain infinite copies of everything, including exact duplicates of you, Earth, and our entire observable region. The laws of probability guarantee that every possible arrangement of matter occurs infinitely many times across infinite space. This leads to the conclusion that infinite versions of you are reading these exact words right now. Even if finite, the universe is almost certainly much larger than we observe. Current measurements suggest that if the universe has positive curvature, It must be at least 400 times larger than our observable bubble. We began this journey standing on what felt like solid ground, convinced we understood the scale of our world. Now we've traveled through distances so vast they break human comprehension, encountered objects so extreme they challenge physics itself, and discovered that everything we can see represents less than nothing compared to cosmic reality's true scope. The universe began smaller than the period at the end of this sentence, then grew larger than we can ever imagine. From neutron stars spinning hundreds of times per second to cosmic structures stretching billions of light-years across, from dark matter that outweighs everything visible, to dark energy ripping space apart, every scale reveals new mysteries. The most humbling realization is this. Despite all our telescopes and theories, we may have glimpsed only an infinitesimal fraction of what exists. Beyond our cosmic horizon lies a universe potentially infinite in extent, containing wonders we cannot imagine. You are standing on a small rock orbiting an average star in an ordinary galaxy, in a universe so large that our entire observable cosmos will be smaller than a single atom if compressed to Earth size. The universe is not just bigger than you imagine. It's bigger than you can imagine. If you want more tips like this, make sure you hit the subscribe button.